In this video, I want to go over a topic that's very common on the SAT, which is exponential functions. Now, it can be exponential growth or decay functions. In this video, I'm going to refresh you on the basics of how these works, or introduce them to you if you've never seen them before. And then I'm going to show you some possible questions from the more straightforward to a little bit more challenging ones. So first, let's take a look at what exponential growth functions are. You can see here I've kind of sketched one, and what you look like, this pattern is where something increases by more and more and more and more, versus where you have something that's linear. Of course, it's going to go up by the same amount or down by the same amount, right? And these kind of look like quadratics, right, where we have y equals x squared, but they're going to have a little bit different shape. And they also don't go up and down. Something like this would actually be here in the negative region for the x. Now, we call them exponential functions because you notice here's an example: f of x equals ab to the x. With exponential functions, the variable, in this case the x, is in the exponent. It's in the power. So that's why we call them exponential functions. Now, here are some examples of some exponential growth and decay formulas you might have run across. Right here, f of x equals a b to the x is a very basic one. And then someone you might run across is a little bit more advanced, where it says AF, that would mean the final amount final, is equal to the amount original, the starting amount. Then we have a parentheses, and notice in here I have a 1 plus or minus r, and it's to a power of t. Okay, so that's also a type of exponential growth or decay function. And what we're talking about here is something. An example would be if I want to find the final amount, let's say it was money, and I started with $1,000, and it grew at, let's say it grows, I invested it and it grows at 10% for every year that I have it in there. So in this case, I would write 1 plus, and then r. In this model, r stands for the rate. Okay, so the rate, which is 10%, but I need to put that in decimal form. So 10% as a decimal is 0.10. So I would put that here, 0.10, and it would be to the power of t. I would simplify this to be 1.1 to the t. This is still the starting amount, 1,000, and I would want to be finding what this is 1,000, what happened to this over time. So if I'm multiplying it every year, t is a year, every year I'm going to keep multiplying it by 1.1, of course it's going to go up over time. That's just an example. But the basic format here is we get a final amount, we start with something, we start with a number, and that is times some rate that is to an exponent. And this can change because we're going to graph it, and we get a different result. So every model I give you is going to have a certain number for A, like this one over here. I said, oh, when it's $1,000, and then the B will be the either rate or decay. So let me give you an example. If I had one that was a decay, that could be, if I'm going to erase this here, if I start with that same $1,000, okay, but this time maybe it's the value of a car, and I want to find out the final value, and the car, instead of growing value 10% per year, cars will often lose their value, they depreciate. So let's say in this case that it loses 10% of its value per year. So when I come to this parentheses over here, I still need to use that 1, but instead of adding the rate, I will be subtracting. I will take away the rate. But the rate here I said is still 10%, but it's a loss, and I need to do that as a decimal, which is 0.10. So taking away r here is 0.10, still to the t. And then when we simplify that, our final amount is going to equal the 1,000 of the original value. And when I do 1 take away 0.10, now I have 0.90. Okay, so you see the difference here? In the first one, this number inside here was greater than 1. When it was adding 10%, that factor in there came out to be 1.1, greater than 1. Now, when I'm losing money, it went down because I subtracted. Now it's less than 1. Now, quick note here, you'll never get anything lower than 0 here. In fact, you will never get 0. This parentheses here, that is never going to be 0, or it'll never be negative. Here's another example of a model, and here I have the function that is f of x equals 2 parentheses 1.5x. Taking a look at this model, let's see what happens to it when x changes. So what I mean is, when, let's say I do a table of values, because don't forget, a table of values is always very helpful when you're trying to figure out some kind of graph. So what happens is I plug in, for this right here, if I plug in a 0. If I plug in 0, then now I'm going to compute that I get 2 parentheses 1.5 to the 0 power. Now remember, anything to the 0 power is just 1. So the 1.5 to the 0 power is 1. So essentially 2 times 1, this is going to be a 1 there, is 2. Plugging in 1 for x. Now I've got the 2, and then it's the 1.5 to the first power, which is, of course, is just 2 times a 1.5 is 3. Then I have, when I plug in a 2, I have the 2 here, 1.5, and then I'm putting in 2 for the x up here. So 2 times 1.5 squared, well, 1.5 squared I know is 2.25 if you do it on your calculator, and double that, this comes out to be a 4.5. Notice how it went up by 1 the first time, now it just went up by 1.5. Try one more value of x at 3. Still have that 2 right here. 1.5 is still in the parentheses, and now the power that I'm replacing x with is 3. Now when I do that, 2 times 1.5 cubed, that actually, that will get me up to, it's 6 point, I believe it's about 6.3 or something. So notice now it went up by about 1.8. So the amount that it's going up by, went up by 1, 1.5, 1.8, the amount that it goes up by actually goes up by more each time. Let's plot this, see what it looks like. So 0 for x, and the f of x, or the y here, is 2. So that's a coordinate of 0, 2. Well, let's put that in here. 0 for x, and a y is 2. This one right here, when I got a 1 for x, I got a 3 for y, 1, 3. Then when I did the 2 for x, we got a 4.50, so 2, 4.50 is the coordinate there. That is, I'm going to go right about there. And then finally when I have 3 and it goes to 6.3, 3 comma 6.3, at 3 then I'm up about here. Now, it's a little rough sketch here, but it's basically getting this idea that it's going up. That's an exponential growth problem. Now let's take a look at the same basic situation, but instead of growth, notice here in my model I have f of x. I still am starting with that 2 coefficient there. Coefficient is the constant number right in front of the parentheses there. So this situation, I have less than 1, 0.5. Remember what I said? If it's less than 1, you're actually going to get a decay. The graph is not going to go up. It's going to start and go something down like that. So let's see what it looks like. Plugging in again for x. If I plug in the 0 here, plugging that in, I use 2 parentheses and then 0.5. That's going to be to the 0, and again, anything to the 0 is 1, so we're really talking about just 2 right there. And then plugging in 1, you have 2 parentheses 0.5 to the first power. 0.5 to the first power is itself, so 2 times 0.5, I get a 1. See how it's going down. Next one, I'm going to plug in 2 for the exponent, 0.5 squared. 0.5 squared is actually 0.25 times 2 is 1/2. So this decreased by 1, but this only decreased by 1/2. So it's actually slowing down how much it's decreasing. And then when x is 3, I take that 2, 0.5 to the 3, and when I do that, I actually come out to be that this comes out to be, it's a quarter, okay, so, or 0.25. Let's take a look what that looks like. So when I plugged in 0, I got 2. So 0, 2 is on there. 0, comma 2. Notice I made the f of x axis really extended up because we're starting at 2 and it's going to go down. When I have 1, the coordinate was 1, so 1, 1, which is here. When I plugged in 2 for x, I got 1/2. Let's just call that 2 and then 0.5. 2, and then that's like here, right? 0.5. So that's going to be right about there. And then when I plugged in 3, I got a quarter, so that's 3, 0.25. So over here, it's right about there. Notice how, yes, it's decreasing, but the amount kind of gets less steep. It's decreasing by less and less. Because see, here it went down by 1, then it went down by 1/2, and then from here, when it was 1/2 to 1/4, it just basically lost 1/4. So the amount it's decreasing is getting less and less. But the key point is here is that in both of these, if you look back at this one, this started at a 2, that was my y-intercept. And then because it was greater than 1, it went up. Here, when it started at a 2, it's still the y-intercept. But because it's less than 1, it goes down. So that's how these work. So to review here, this over here where they say f of x, sometimes they'll say a final, they may say it may be p of x or p of time for population over time. Whatever it is, it doesn't matter. When it's the only thing on the left side of this equal sign in an exponential problem will be the final amount. And I say by final amount, I mean when you tell me what you want to plug in for the x, then I can tell you what the final result is. And then right after the equal sign, this number here, that coefficient, is always the starting amount, always. So right there, you know you can count on those to be that. And then what comes immediately after this will be this right here. And that is going to be the growth rate or the decay, as we talked about, whether it's above 1 or less than 1. And then finally, that's always going to be raised to a power. Now, the power a lot of times is x, but as I said, sometimes they'll do like the population in a town over time equals, maybe they start with 2,000 people and it has a growth rate of maybe it goes up by 25%. And then we say to the t years. So maybe we can track a population over time. But it's always the basic same idea. Your final amount equals your starting amount. Then right here, final amount, starting amount, some kind of growth rate, and it depends on the time or the year you give me. Let's take a look at a little bit more complicated. The way they do this is the SAT. Yeah, so look at this. So here's an example. Go here. This is a very straightforward question. This would be not very challenging one. And this says the model function says the p of t equals the 1,250, 0.03. I would have put this here to the power of t. And then what I've got is, so I've got the final amount that I want. I have the starting amount. Notice here that means it's less than 1. In fact, what it really was 1 take away 0.17, right? Because that gives me 0.83. So in this case, this amount is going to go down by 17%. So keep that in mind. If you see this, they'll sometimes ask you that question. The question actually could be, by what percent is this decreasing? And you need to be able to know, okay, it's always 1. If it's less than 1, it's 1 take away some kind of percent. Right here, 1 take away 0.17, that's how I got that 0.83. You could answer a question right there. It is going down by 17%. Okay? If it had said in parentheses 0.92, that means that it was going down by 0.08, right? 0.08, because 1 take away 0.08, well, that's that 0.92. So that's a question they could ask you right in there, so make sure you're familiar with that. Very straightforward question is if they actually have you graph that. Of course, you'd want to go to Desmos and do that. But you can predict it now. We've talked about it. This will be the starting amount. So you should be starting at 1250. And because it's 0.83, it's going to be a decay. And it'll look something like this. If I want to know the exact numbers, well, I could always do a table of values, right? I could put in for T is the X, and I could find the population in T. Or you could just put it in Desmos. Okay, straightforward one. Watch the twist they'll put on this. Now, notice I have the same thing here, population 1250, 0.83 T. However, here, I do have the population, and I do have 0.03, and it's to a certain amount of time. And they'll ask you this way. The function given represents the population of Bakersville, where T represents the number of years since 1983. Okay, and then what they're looking for is they want you to understand that it's a decay, okay, but off this they could ask a question such as what would be the beginning population, and or what could be what they might say, what does the graph look like? So they'll give you some choices. So how are you supposed to figure out what the graph looks like if you can't plug this into Desmos, right? Because you can plug in, for the Desmos, you plug in a y equals, and you can have a variable like x, often x, but really that means just t. The point is that the x-axis here, in this case, it's a t. And you do have this number, but it's like a third variable, okay? But it really isn't. What they're doing is they're hiding it on you. And so what do we remember about this spot? Remember, that's the beginning point. So they want you to be able to, maybe they graph this, maybe they put in M here, and then they put in, maybe they put in 0.5 M, or they could even do, this one could be 0.83 M or something like that, and then they have an M, and maybe they have a in this graph, well, we know that it starts at M, the y-intercept is M, but maybe they make that graph go up. But you can rule that out because this is less than 1, so it's decay, so I'm getting rid of that. Now maybe they put it here and then do decay, okay, but that's not what the y-intercept is. It is straight out M in this problem. We don't know what it is, but don't let that freak you out. What we do know is that it starts at M and it decays, okay? So you can kind of, knowing how these work, you'll be able to get that one. Okay, so here we have one that's saying the function models. This function models the grams of a radioactive substance remaining after T years. Which of the following could be a coordinate on the graph of the function? So here we go. They're not asking you a straightforward exponential question like you might expect in school. What we need to know, we need to take a look at what we know about functional, exponential functions. Okay. Without even, now this is a little bit stranger here because you do recognize, this is the final amount here, and I have a starting amount here, and I've got some kind of information here, although it didn't give me a number. And you may recognize there's a t, but this is a little bit strange, right? Why do I have negative k in there? Something like this, don't panic. Use the table of values as your friend, Okay, so what I mean by that is the little table of values here, I can kind of figure out when you put in for t here, when I put into this function, if I put in, what if I make t equals 0? Okay, so I'm kind of like t equals 0. What am I going to get for the function? Well, let's look. The value of that function is going to equal a parentheses b negative k. I know it's a lot of things I don't know, but if I make t 0, what does that do? Well, of course, this power here, the negative k times 0, I'm going to get rid of that because that's just going to be 0, right? Anything times 0. This is to the 0 power. All right. This is to the 0 power, and anything to the 0 power, well, that's just 1. So now I just have a times 1, which of course is a. So what happened was when I put in 0 for t, the result was a. Now, t is like my x, and this is my y. So I have a coordinate right here. When t is 0, then the y value, or the f of x, is a. So that is a definite coordinate. And this is sometimes what freaks people out in the SAT is, well, that's not a number, 0a. But you got to get used to these if you're going to get the really difficult, challenging problems on the SAT. Okay, so 0, comma a, that's right there.